It gives us an opportunity to prove that we can manufacture these sodium-ion batteries on lithium-ion lines before we then go out and build a global scale plant.
A new AI-powered sodium battery might be the answer to some of the biggest challenges in the EV world. With the potential to lower costs, increase efficiency, and reduce dependence on lithium, this innovation could make electric vehicles more accessible and sustainable. As the industry evolves, this technology might set a new standard for EV energy storage. In this video, we're going to get to the bottom of just how it's all going down. The need for a new era of batteries. The EV industry is growing at an unprecedented pace, driving the demand for efficient, scalable energy storage solutions. Lithium-ion batteries have dominated the landscape because of their high energy density and efficiency. They've proven reliable for powering EVs, smartphones, and even large-scale energy grids. But while lithium-ion batteries power everything from smartphones to electric vehicles, their growth has introduced several complex challenges, both economic and environmental. One major challenge is the rapid rise in lithium prices. Over the last few years, demand for lithium has surged, largely driven by the booming electric vehicle market. As the auto industry moves toward electric vehicles, lithium is essential for powering their batteries. However, lithium production hasn't kept pace with the increasing demand, which has led to significant price hikes. Some lithium prices have gone up by as much as 400% in the past 2 years. The price spike is due to a combination of factors. Extracting lithium, whether from brines or mines, requires a great deal of time, labor, and energy. Most of the world's lithium supplies come from remote locations like the Lithium Triangle, made up of Argentina, Chile, and Bolivia, or from harsh environments in places like Australia and China. The difficulty of ramping up production and meeting growing demand creates a supply bottleneck that drives prices higher and makes them harder to predict. While lithium mining brings huge financial benefits, it also creates severe environmental problems. One of the biggest issues is the large amount of water needed to extract lithium, especially from brines in salt flats. In areas like the Lithium Triangle, miners must pump up vast amounts of water and allow it to evaporate before extracting the lithium. This method depletes the water sources that are critical to the local communities, who rely on those supplies for drinking and farming. In fact, in places like Chile, the growing lithium industry has already led to water shortages that hurt local populations. Besides depleting water resources, lithium mining can destroy entire ecosystems. As lithium operations expand, they disturb land and wildlife, often within delicate habitats. Indigenous species face the risk of extinction, and large-scale mining operations have led to increased carbon emissions, undermining the environmentally friendly claims made about electric vehicles. Lithium extraction is concentrated in only a few countries, particularly Australia, Chile, and China. This creates significant risks to supply chain security. If political instability or trade restrictions impact lithium-producing nations, it could disrupt global supply, leading to price hikes or shortages for other regions. Countries that rely on lithium imports, particularly in Europe and North America, become vulnerable to the decisions of major lithium-producing countries. Relying so heavily on lithium production from specific geopolitical regions places the world's energy transition at risk. China, which controls much of the refining and processing of lithium, could influence prices and global distribution. Countries looking to reduce dependence on China may struggle with supply challenges as they try to secure a more diversified supply of lithium. As the demand for electric vehicles continues to rise, lithium-related issues have worsened. Governments around the world are pushing for a shift toward greener alternatives, but the demand for lithium has also escalated significantly. This surge in electric vehicle production has fueled the global demand for lithium, making supply problems and high prices even worse. The electric vehicle market's reliance on lithium for battery production has led to increasing pressure on the mining industry. If the demand for electric vehicles continues to grow, lithium supply must expand at the same rate. But it's unclear whether the global lithium industry can keep up with both demand and rising prices, or how this growth will be affected by limited supplies of the metal. These difficulties further complicate the energy transition, as the lithium needed to fuel electric vehicles becomes a more costly and difficult commodity to obtain. In conclusion, while lithium plays a vital role in powering the green revolution, its rising prices, environmental impacts, supply bottlenecks, and growing demand from the electric vehicle market all raise concerns. These ongoing issues are prompting many to seek alternative energy storage solutions, especially sodium-ion batteries. These alternatives could provide a more affordable, sustainable solution for the future of energy storage. Sodium as a solution. Sodium offers a major advantage over lithium in terms of abundance. While lithium is concentrated in only a few regions around the world, sodium is found almost everywhere. Most notably, seawater contains vast amounts of sodium, making it far more accessible and easier to obtain. This widespread availability significantly reduces the risk of shortages or supply chain issues that often affect lithium. Unlike lithium, which requires extensive mining and extraction processes, sodium's abundance ensures a more stable and reliable source for future energy storage needs. Sodium's cost-effectiveness further strengthens its potential as a sustainable alternative to lithium. Sodium is about 50 times cheaper than lithium, which makes it a compelling option, especially as global demand for energy storage continues to rise. While lithium's high cost has driven up prices in industries like electric vehicles and renewable energy storage, sodium's affordability can dramatically lower production costs for batteries and make energy storage solutions more accessible to both businesses and consumers. The environmental impact of sodium extraction is another key factor in its favor. Unlike lithium, which requires extensive mining that degrades the environment, sodium can be sustainably harvested from seawater without causing significant harm. Lithium mining, particularly in areas like the Lithium Triangle in South America, depletes crucial water supplies, disrupts local ecosystems, and leads to other environmental degradation. Sodium, on the other hand, doesn't require destructive extraction processes, making it a more eco-friendly option. By switching to sodium, we can reduce the environmental damage caused by battery production while maintaining high energy storage capacity. Sodium's key properties also make it a strong contender for use in batteries. Sodium ions can move freely and efficiently within the battery, similar to lithium ions in conventional lithium-ion batteries. While sodium-ion batteries have traditionally had lower energy densities compared to lithium batteries, recent innovations have improved their performance. Sodium batteries have reached energy densities that are comparable to lithium batteries, thanks in part to new materials like sodium vanadium phosphate. These advances have made sodium batteries more competitive and suitable for a variety of applications, from consumer electronics to electric vehicles. In addition to being cheaper and more environmentally friendly, sodium is also safer. Sodium-ion batteries are less prone to overheating or catching fire, making them inherently safer than some lithium-based alternatives. These properties make sodium a viable and attractive solution for the future of energy storage, offering a more sustainable and affordable alternative to lithium while maintaining high performance. Advancements in sodium-ion battery technology. Sodium-ion batteries, while initially promising, faced a number of obstacles that prevented them from gaining traction as a viable alternative to lithium-ion batteries. One of the most significant issues was their relatively low energy density. Historically, sodium batteries offered roughly 10 to 20% less energy capacity than their lithium counterparts. While this difference may seem minimal, it was enough to limit their application, especially in areas requiring high energy output, like electric vehicles and grid-scale energy storage. Another problem lay in the instability of sodium batteries during energy discharge. During the charge and discharge cycles, sodium ions have struggled to move effectively, resulting in a higher likelihood of performance dips and inefficient energy release. This led to reduced battery lifespans and an overall decline in performance. Early efforts to scale sodium-ion technology also failed to produce consistently reliable results, which limited its use to niche applications or remained purely theoretical. As a result, the development of sodium batteries hit a roadblock as the technology couldn't compete with the established lithium-ion batteries that were already at the forefront of the market. Recently, however, sodium-ion battery technology has started to break through these limitations thanks to advancements in materials science and electrochemistry. One of the key developments has been the creation of sodium vanadium phosphate, a material that has significantly improved the energy density of sodium-ion batteries. This material has allowed sodium batteries to push the boundaries of their previous limitations, particularly in terms of storage capacity. While earlier versions of sodium batteries had an energy density of around 458 watt-hour per kilogram. Breakthroughs have seen this figure increase to over 2200 watt-hour per kilogram. Such an improvement in energy density brings sodium-ion batteries closer to competing directly with lithium-ion batteries for large-scale energy storage and electric vehicle applications. Additionally, researchers have successfully improved the charge-discharge cycles in sodium-ion batteries, which directly translates to higher efficiency. With improved cycle stability, sodium batteries now perform more reliably, and their lifespan has dramatically increased. In practical terms, this means fewer replacements are necessary, making them both cost-effective and efficient in long-term energy solutions. Better charge-discharge cycles also indicate that sodium batteries will be less prone to degradation with repeated use, which has been a major issue for earlier prototypes and some lithium-ion batteries as well. The cumulative effect of these recent breakthroughs has made sodium-ion batteries not only more energy efficient, but also more versatile in a range of applications. Whether for energy storage solutions or for renewable energy integration, sodium batteries are steadily proving their worth as a more sustainable, affordable alternative to lithium technology. Real-world case studies show the practical capabilities of sodium-ion batteries and helping to validate their potential. One noteworthy example comes from Australia, where the country installed its first large-scale sodium battery energy storage system. This system represents a major milestone in the deployment of sodium-ion batteries outside the laboratory environment. It proves that sodium-ion technology is no longer just theoretical or experimental. It's becoming a practical and reliable solution for tackling energy storage challenges. By providing a more sustainable and cost-effective way to store excess renewable energy, sodium-ion batteries offer an alternative that could potentially reshape how communities and industries manage energy storage. In addition to this first large-scale installation, there are numerous laboratory success stories that highlight further developments in sodium-ion technology. Research labs worldwide are consistently achieving new breakthroughs in energy storage, many of which have shown that sodium-ion batteries can now store energy more efficiently, be recharged faster, and last much longer without performance issues. As the technology continues to evolve, the road to commercial deployment is becoming much clearer, with manufacturers scaling up production and real-world implementation becoming more feasible with every passing year. How sodium batteries work. Sodium-ion batteries operate similarly to lithium-ion batteries, but use sodium ions instead of lithium ions to store and release energy. At the core of a sodium battery is an electrochemical process. When the battery charges, sodium ions are stored in the battery's anode, usually made from carbon or other porous materials. During discharge, these sodium ions move from the anode to the cathode, which is usually made from materials like transition metal oxides, through the electrolyte. As the ions travel, they create an electric current that powers the connected device, whether it's an electric vehicle, a phone, or an energy storage system. This process of energy storage and discharge relies on the movement of sodium ions within the battery's internal structure. As sodium ions are pushed back and forth during charging and discharging cycles, they release or absorb energy in the form of electrons, which is the current that powers electronic devices. While the fundamental mechanism between sodium-ion and lithium-ion batteries is the same, the main difference lies in the materials and the properties of the ions involved. While sodium and lithium-ion batteries work on similar principles, several key differences separate the two technologies. The most obvious difference is the type of ion used for energy transfer. Lithium-ion batteries use lithium ions, which are much smaller and lighter than sodium ions. This gives lithium-ion batteries their higher energy density. The smaller size of lithium ions allows them to pack more tightly into the battery's anode and cathode, which results in greater energy storage and a higher overall energy output. Sodium ions, on the other hand, are larger and heavier. This size difference presents a challenge for sodium-ion batteries, as the larger ions take up more space and are less efficient at moving through the battery's internal structures. The increase in size also means that sodium-ion batteries typically have a lower energy density compared to lithium-ion batteries. However, sodium is more abundant and cheaper than lithium, making it a more cost-effective option for mass production, despite the energy density trade-off. The chemical properties of sodium ions also affect how the batteries behave over time. While lithium-ion batteries can often be prone to degradation over many charge cycles, recent advancements in sodium battery design have managed to significantly improve their stability and lifespan. This has enabled sodium-ion batteries to take on more of the market's energy storage demands without as much worry about long-term performance issues. For sodium-ion technology to be commercially viable, it required breakthroughs in several key areas, particularly the movement and stability of sodium ions. One of the main challenges with sodium-ion batteries has been ensuring the efficient flow of sodium ions through the battery during charge and discharge cycles. In the past, sodium ions would move too slowly or unevenly, leading to inefficiencies and loss of performance over time. To address this, several innovative approaches have emerged. One of the most significant breakthroughs has been the use of improved materials for the anodes and cathodes. Researchers have developed new materials that offer better ion transport and enhanced energy storage properties. For example, materials such as sodium vanadium phosphate have allowed for more efficient sodium-ion movement, helping increase the overall energy density of the battery. The development of more conductive and flexible electrolytes has also played a critical role. These electrolytes help sodium ions move more freely within the battery, improving charge and discharge speeds. This innovation also helps stabilize the battery, leading to fewer issues related to performance degradation or inefficiency over time. Furthermore, better understanding of the physical properties of sodium ions at the atomic level has led to improved electrode structures. Researchers have been working on optimizing the surface area of anodes and cathodes to ensure that more sodium ions can fit into the available space. These innovations are key to making sodium-ion batteries a serious alternative to lithium-ion batteries, particularly for applications requiring long-term stability and cost efficiency. As more research is done and new breakthroughs continue to emerge, the gap between sodium-ion and lithium-ion technology is closing. Sodium batteries, once considered impractical due to their limitations, are evolving into a viable solution, with increased sodium-ion mobility helping them better compete with lithium-based technology on both performance and cost. Cost and sustainability. Benefits of sodium batteries. One of the key advantages of sodium-ion batteries lies in their significantly lower environmental impact compared to lithium-ion batteries. While lithium-ion battery production relies on mining rare earth metals like lithium, cobalt, and nickel, sodium is abundantly available in seawater and salt deposits around the world. Sodium mining, unlike lithium mining, requires far fewer resources and causes considerably less environmental damage. This helps reduce the environmental degradation that typically comes with mining for precious metals. Lithium mining has been linked to deforestation, water depletion, and chemical pollution, often affecting ecosystems and local communities. On the other hand, the mining and extraction process for sodium poses less threat to land and water systems. As sodium is widely distributed and easier to extract, the environmental footprint associated with sodium-ion battery production is considerably smaller. This can significantly lower the overall environmental cost of energy storage solutions on a global scale. Sodium-ion batteries present a major advantage in terms of production costs. Sodium itself is about 50 times cheaper than lithium, thanks to its abundant availability and the simplicity of its extraction processes. Sodium-ion batteries can, therefore, be produced at a fraction of the cost compared to their lithium counterparts. This reduction in raw material costs is just one factor that makes sodium-ion technology appealing for large-scale use. Manufacturers can potentially pass these savings on to consumers, making energy storage more affordable. Additionally, sodium-ion batteries can use existing infrastructure and manufacturing techniques designed for lithium-ion batteries, which can further reduce costs by minimizing the need for new facilities or complicated production processes. This cost advantage is particularly relevant in applications where price sensitivity is a key concern, such as in large-scale energy storage or budget-conscious markets. By making energy storage more affordable, sodium-ion batteries could have a significant impact on global energy access, particularly in regions where the cost of traditional energy storage is prohibitive. Sodium-ion batteries also offer flexibility in terms of scalability. The same technological advancements that improve performance for small electronic devices, such as laptops or smartphones, can also be applied to much larger applications, such as grid storage for renewable energy or electric vehicles. As sodium is inexpensive and abundant, scaling up production for both small and large devices doesn't involve the same costs and challenges associated with lithium-ion battery systems. For large-scale applications, like renewable energy grids or storage systems for solar and wind power, the scalability of sodium-ion batteries is an attractive proposition. Grid-scale energy storage is essential for smoothing out intermittent supply and demand issues posed by renewable energy sources. Sodium-ion batteries' scalability offers the potential to provide cost-effective, large-scale storage solutions that can store energy when conditions are ideal and discharge it when needed. For smaller applications, such as portable electronics or off-grid solutions, sodium-ion technology can still provide the necessary power capacity without the high cost typically seen in lithium batteries. This combination of cost efficiency and adaptability makes sodium-ion batteries a promising solution for various markets and industries. Another important benefit of sodium-ion batteries is their potential to help democratize energy storage, particularly in developing regions. As sodium-ion batteries become more affordable and scalable, they can be used to provide clean energy storage solutions in areas with limited infrastructure or unreliable access to traditional electricity grids. In many parts of the world, particularly in rural and off-grid communities, energy storage systems are the key to accessing renewable energy. However, the high costs of lithium-based batteries often prevent these regions from taking full advantage of solar, wind, or other green energy sources. Sodium-ion batteries' affordability and ease of deployment provide an opportunity to bridge this gap, giving many underserved regions access to clean, reliable, and cost-effective energy storage. This widespread availability of affordable energy storage could lead to improved energy security, promote the use of renewable energy, and help drive sustainable development. It could also stimulate economic growth in developing areas, as these communities gain more control over their energy resources and reduce their dependence on fossil fuels or expensive imported energy. Longevity and performance advantages. One of the major advantages of sodium-ion batteries is their exceptional lifespan. While lithium-ion batteries typically last between 5 to 10 years, sodium-ion batteries have the potential to last much longer, with estimates suggesting they can remain functional for up to 50 years. This extended lifespan is particularly valuable in applications where long-term reliability and minimal maintenance are essential, such as in large-scale energy storage or in infrastructure supporting critical energy systems. Sodium stability and chemical properties allow the battery cells to maintain their charge and function effectively over a longer period, even with regular cycles of charging and discharging. The longevity of sodium-ion batteries reduces the frequency of replacements, making them a more cost-effective option over time, especially for applications with large-scale energy needs. With fewer replacements required, sodium-ion batteries not only provide significant economic savings, but also contribute to a reduction in electronic waste. Since sodium-ion batteries are likely to last much longer than lithium-ion batteries, the need for replacements is reduced. This lower replacement rate not only saves money over time, but also plays a role in tackling the growing issue of electronic waste. The shorter lifespan of traditional lithium-ion batteries has contributed to the increasing pileup of e-waste, which is an environmental problem that is hard to ignore. The durability of sodium-ion batteries addresses some of these concerns. As their lifespan potentially spans multiple decades, fewer batteries will be disposed of, reducing the strain on waste management systems and lessening the need for raw materials to produce new batteries. This environmentally friendly advantage aligns well with global sustainability goals, helping decrease the ecological impact of battery disposal. As electronic waste has become a major environmental challenge, long-lasting sodium-ion batteries offer a welcome solution to help curb the growing problem of discarded battery products. Sodium-ion batteries also have the benefit of providing consistent voltage output throughout their lifespan, ensuring reliable performance even in applications with varying energy demands. This continuous voltage delivery is crucial in many energy-intensive scenarios, including powering electric vehicles, renewable energy storage, and even consumer electronics. Unlike some battery types that experience a noticeable drop in performance over time, leading to issues like reduced power output or shortened operation times. Sodium-ion batteries tend to maintain a steady level of energy delivery throughout their life. This ensures that users can count on consistent battery performance for longer periods, reducing the frequency of power outages or energy loss and improving the overall user experience. In large-scale energy applications, where grid stability depends on reliable and uninterrupted power sources, sodium-ion batteries' ability to deliver dependable voltage over extended periods adds significant value. Their performance reliability makes them an ideal choice for regions and industries seeking to build resilient and sustainable energy storage solutions. Despite these promising longevity and performance benefits, sodium-ion batteries do face challenges in achieving commercial-level durability. One major hurdle is the need for continued research and development to refine their cycle life. Essentially, the number of charge-discharge cycles the battery can undergo before losing significant capacity. While sodium-ion batteries have made significant strides in terms of energy efficiency, cycling stability, and longevity, improving their commercial durability remains an ongoing process. Researchers continue to explore ways to optimize sodium-ion battery performance by enhancing material structures and improving the way sodium ions interact within the cells. Additionally, scaling sodium-ion battery production to meet global demand while maintaining consistent durability across millions of units is no small task. Manufacturers will need to overcome various technical challenges to ensure sodium-ion batteries retain their longevity and performance characteristics under real-world conditions. That said, with ongoing advances in battery chemistry and materials science, these challenges are likely to be addressed in time. Once commercial durability reaches its full potential, sodium-ion batteries could offer an even more competitive alternative to lithium-ion systems in a variety of applications, helping users unlock even greater savings, sustainability, and reliability. In conclusion, sodium-ion batteries stand out for their impressive longevity, stable performance, and environmental advantages. Though there are still hurdles to overcome in achieving commercial-level durability, their lifespan, low replacement rates, and steady voltage delivery position them as a promising technology with potential for long-term and large-scale adoption. Applications of sodium batteries in the EV industry. Sodium-ion batteries have the potential to significantly alter the electric vehicle industry by replacing the more commonly used lithium-ion batteries. These batteries are considered a viable alternative due to their ability to offer similar performance in terms of power storage and charging speed, while being much more cost-effective. Given that sodium is far more abundant and less expensive than lithium, this could result in considerable cost savings for EV manufacturers and consumers. In terms of energy output, sodium-ion batteries have improved over the years, with recent advancements closing the gap with lithium-ion cells in terms of energy density. While sodium-ion batteries typically have slightly lower energy density, they still offer a powerful energy storage capacity for vehicles, particularly as advancements in sodium battery technology continue to make them more efficient. This makes them a strong contender for EV manufacturers looking to cut costs while still delivering reliable performance. Sodium batteries also outperform lithium-ion batteries in terms of environmental impact. Lithium mining has come under scrutiny for its environmental toll, especially in areas where water resources are already scarce. In contrast, sodium extraction doesn't require the intensive resource management and water usage that lithium does. Therefore, sodium-ion batteries offer a more sustainable alternative, helping reduce the carbon footprint of EVs. By replacing lithium-ion batteries with sodium-ion batteries, EV manufacturers could potentially lower production costs while offering an environmentally friendly vehicle alternative that doesn't sacrifice performance or range. Renewable energy integration, wind and solar energy storage. Another significant application of sodium-ion batteries lies in renewable energy storage. Wind and solar energy are highly variable, meaning that power generation doesn't always align with demand. Sodium-ion batteries, with their ability to store large amounts of energy at a low cost, provide an efficient means of storing excess energy generated by wind and solar systems. Once the energy is stored, it can be used when production from renewable sources is low or demand is high. The scalability and long lifespan of sodium-ion batteries make them an ideal solution for large-scale renewable energy storage. These batteries can be used to stabilize the grid, supporting a smoother integration of intermittent renewable energy sources and allowing more communities to benefit from clean energy. By using sodium-ion batteries in conjunction with renewable energy sources, it's possible to create a more resilient and sustainable energy grid. The low cost of sodium-ion batteries also makes this solution more accessible, especially in developing regions where the cost of energy storage could otherwise be prohibitive. Grid-level implementations for community energy stability. At the grid level, sodium-ion batteries have the potential to provide communities with stable, reliable energy, particularly in off-grid or rural locations. Since these batteries can store large amounts of electricity, they can serve as an efficient backup power source, ensuring communities have reliable access to energy, even during blackouts or high-demand periods. These grid-level implementations could be crucial for enhancing energy stability in communities that rely on older, less reliable electrical infrastructure. Sodium-ion batteries have a particular advantage when it comes to scalability for community-level energy projects. Their relatively low cost and long lifespan could reduce the need for frequent maintenance or battery replacements, making it easier to implement large-scale storage systems without a significant financial burden on local governments or communities. This could contribute to improved energy security in underserved areas and make grid stability achievable in rural regions where solar or wind power might otherwise be the primary source of electricity. Consumer electronics and other potential markets. Sodium-ion batteries also present an opportunity for broader integration into consumer electronics, such as smartphones, laptops, and even electric bikes. These applications would benefit from the long lifespan and cost-effectiveness that sodium-ion technology offers. Additionally, industries looking for energy storage solutions for smaller devices could utilize sodium batteries to lower overall production costs while maintaining high levels of reliability. The consumer electronics market has already begun to explore alternatives to traditional lithium-ion batteries, particularly when it comes to reducing environmental footprints. Sodium-ion batteries, with their reduced environmental impact and potential cost savings, are well suited to address these needs. Moreover, sodium batteries' versatility extends beyond just these industries. Their potential could span even further, incorporating energy solutions in industrial tools, backup systems, and energy grids. Over time, as research into sodium-ion battery technology advances, it's likely that more uses and applications will emerge, solidifying the technology as a foundational energy storage solution for both household and commercial use. Sodium-ion batteries are going to make a significant impact not only in the electric vehicle sector, but also across various other industries. Their cost-effectiveness, sustainability, and versatility open up possibilities for renewable energy storage, grid-level energy stability, and even consumer electronics. But could it actually take over the original lithium batteries we know and love? What do you think? Leave your thoughts in the comments below, and if you like this video, don't forget to subscribe to our channel. See you in the next one.